My name is Masharia from Thika High School. I teach maths and chemistry. And I want us to go through the very first topic in the Form 4 syllabus, the topic acid, bases, and salt. And I believe that this is not the very first thing that you are coming across the terms acid, bases, and probably salts, because we started interacting with the same way back in Form 1, even before we go to high school. When we were in Form 1, we defined acid. There was a topic that we called acid, bases, and indicators. And in that first topic, we said, and the word acid is derived from the word acidus. And acidus means sour. So we started by defining an acid as a substance that has a sour taste. Bases was then said to be a substance that has a soapy feel, that when you put sodium hydroxide, when you touch sodium hydroxide, you feel that it will have a soapy feel. Definitely, it's actually a soap that has been formed, because as you shall discover later on in the course, fats will react with sodium hydroxide to form a salt that is called a soap. And your hands must be fatty, there must be some fat in your hands. So that is what is reacting with the sodium hydroxide to form a salt, and to form a soap, and that's why there is a soapy feel. So you realize from that small exposure that the sodium hydroxide is reacting with your hand. Therefore, that is not a very good test for bases. Similarly, many of the acids are going to be corrosive. You cannot, for instance, test sulfuric 6 acid. You're going to leave your tongue right there. So it's a very reckless test, although you could say. So we moved a step further. We defined an acid as a substance, acids and bases with respect to what they do with indicators. And we came up with a set of indicators: methyl, orate, we came up with phenolphthalein and litmus. And therefore, one of the most basic definition at that point was an acid is a substance that turns a blue litmus paper red, and a base will be a substance that turns a red litmus paper blue. Now, and that definition worked for a bit of time, until then we went deeper into the study of acids and bases. We came up with some chemical reaction that involves acids, their reactions with metals, their reactions with carbonate, their reactions with bases. And it's on that basis that we defined an acid as a substance that reacts with a metal to produce hydrogen gas. And a salt, of course. A parent definition for a base in terms of its properties, it was defined as a substance that reacts with an acid to form a salt and water only. And that is a reaction that we defined, that we described as neutralization. A reaction between an acid and a base to form a salt and water only. Now, and that is, so we have a few examples. From that definition, we came up with a few examples of acids, and all these can be referred to as mineral acids. So we have quite a number of other acids. Now, bases, we have all metal oxide and hydroxides were defined as bases. Remember, we said that if a base dissolves in water, then it's going to be an alkali. So an alkali is simply a soluble base. We have quite just a handful: sodium hydroxide, potassium hydroxide, ammonium hydroxide, and to a very small extent, calcium hydroxide is a soluble base. Now, I want us to find out something, because it is from whatever this test that we are going to even come up with an even more comprehensive definition of an acid. Because is it dependent on the condition? Will as an acid, whichever form, will all acids react with metals to produce hydrogen in a salt? Does it depend on what you dissolve it in for it to react with an acid? So because from that, if we discover that there's times when a substance that is called an acid yet to not react with a metal to form hydrogen gas, then you may have to improve our definition of acid. Let's briefly look at that.
Hello viewers, with me is oxalic acid, and as the name suggests, this is an organic acid, and I want to find out whether it retains its acidic property irrespective of the solvent in which we dissolve. So I have weighed some ethanoic acid, put them in beakers here.
That is oxalic acid,
dissolve
not
a
ethanol.
portion of ethanol and another portion in water. And I will find out the nature of the solution that is obtained from that. So let's proceed to add ethanol to a portion of this is tap water, and I add tap water to oxalic acid, and similarly with acid in water. So the first test I want to carry out is maybe I will start by introducing a piece of magnesium ribbon into the tube. Here we are, a piece of magnesium ribbon introduced into the two solution. Yes, and there is some rapid reaction there. Some viewers, you can hear some.
Yeah, we can hear some fizzing.
Therefore the solution reacts with metals to produce hydrogen gas. Now on the other hand, the solution in ethanol does not appear to be producing any sodium hydrogen carbonate, and I will put the sodium hydrogen carbonate into the two solutions. The solution of oxalic acid in ethanol first, right? And it just sinks to the bottom. Apparently, there is no reaction when the ethanoic acid is dissolved, or the maleic acid is dissolved in ethanol. But when this is fast reaction, fast effervescence are produced.
Looked at a substance that we would refer to as an acid, an organic acid, that is oxalic acid. But you've discovered that when you put it in an organic solvent, it doesn't appear to have any acidic property. When you put it in ethanol, when you dissolve it in ethanol, it doesn't appear to have any acidic property. We could also draw a parallel with hydrogen chloride. So hydrogen chloride can also be dissolved in water and also in an organic solvent. Now, if you investigate the two solutions, you'll discover that the solution in water has acidic properties. It will change a blue litmus paper red. It will produce bubbles with magnesium. It will produce bubbles with carbon 4 oxide. But when you dissolve it in water, in an organic solvent like methyl benzene, it will not have any acidic property. Yes, we are talking about an acid, a substance that we defined in Form 1 as a substance that reacts with metals to form a salt and hydrogen. But you see, it is not reacting. It is not reacting with the metals if it is dissolved in an organic solvent. So it appears that we may have to build on that definition so that we can account for those properties. And there is one other property of the two solutions that is very telling, so that we shall be able to actually explain why this solution does not have any acidic character this solution does not have, this solution in water has acidic character. Let's look at the electrical conductivity of
acid in water, and on the other side I have a solution of oxalic acid in ethanol. And I want to find out whether the solutions conduct an electric current. Now, if you light the bulb, you light the solution of oxalic in water, therefore conduct an electric current. I introduce it into the solution, it does not. So a solution of oxalic acid in ethanol does not conduct.
all right, and therefore we realize that, and that is an important observation, that the solution in water conduct an electric current. The solution in methyl benzene or ethanol is not conducting an electric current. Now remember that the conductivity in a solution is due to what we refer to as mobile ions, strictly, because the conductivity in metals is due to delocalized electrons, but the conductivity in solution is due to mobile ions. So it only means that the solution of the ethanoic acid, the maleic acid, the oxalic acid, the hydrogen chloride in an organic solvent does not contain mobile ions. That is why it's not conducting. The solution in water contains mobile ions. Now we seek to explain why the solution in water contains mobile ions, and this is what we need to note, that we can classify solvent as either polar or non-polar. What is a polar solvent? A polar solvent is one that contains partial charges. So it is something that is in between ionic and covalent, because an ionic substance must have complete charges. A covalent substance must have no charges at all. Then you have some substances in between that have partial charges. We refer to them as polar substances. Where does polarity result from? It results from differences in electronegativity, where we define electronegativity as a tendency to pull bonded electron, as opposed to when the electrons are completely transferred. When a substance gains an electron, then the energy involved there is referred to as the electron affinity. So electronegativity has nothing to do with transfer. It has all to do with just pulling bonded electrons. So oxygen has a greater tendency to pull bonded electrons towards itself than hydrogen. So the electrons spend more time on the oxygen, making it partially negative. Similarly, chlorine has a greater electronegativity than hydrogen. It will pull the electrons towards itself. So what will therefore happen when you put hydrogen chloride in a polar solvent? So when hydrogen chloride is dissolved in water, the negative end of the water is attracted to the positive end of the hydrogen chloride. In that case, the hydrogen is attracted to the oxygen. Now, because this negative, that is positive. Similarly, the hydrogen is attached to the chloride ion, and then that attachment produces energy. It's a bond formation process. It produces energy, and that energy leads to the breaking of that bond. Also, you could visualize that this one is pulling that direction, this one is also pulling that direction. That leads to the breaking of that bond. So what has happened is that the hydrogen chloride has ionized. It has dissociated. It has broken down to hydrogen ions and the chloride ions. And the same will be surrounded by water molecule, so we can write them like this, like that, where we have a chloride attached to hydrogen ions, surrounded by hydrogen ions, in a process that we refer to as hydration, in the hydration reaction. Now it is these hydrogen ions that have been formed when this is broken. Of course, they will be combined with the water molecule to form a hydroxonium ion. and this is what is responsible for the acidity. So a substance is never going to be acidic unless it has ions. Now, of course, again, it is the formation of these ions that is responsible for the conductivity of the resultants, the hydrogen ions, the marate. You dissolve ammonia in water, it will have basic properties. Why? Because it will dissociate into the ammonium ions and the hydroxide ions. So that will be basic. But when you dissolve it in an organic solvent, it will have no basic properties. Why? Because it will exist in form of molecules, because this solvent are not able to ionize it into that. So we now come up with a better definition. We come up with a better definition of acid and bases, because if we initially said that an acid will react with it, but you have discovered that it's not until you dissolve it in water. So we want to bring in that idea in our definition of an acid. So we define acid as a substance which dissociates in water to produce hydrogen ions as the only positive ions. So the only a substance dissolved when dissolved in water dissociates to give hydrogen ions as the only positive ions. I want to hasten to say that there are some substances that, like aluminium chloride, that dissolves in water to form an acidic solution, yet it's not an acid. Why? Because apart from the hydrogen ions, it will produce aluminium ions. So the hydrogen ions are not the only positive ions. So it forms an acidic solution, but it's not an acid. Now, similarly, a base will be defined as a substance which, when dissolved in water, produce the hydroxide ions as the only negatively charged ions, Remember, we are talking about soluble bases. So a soluble base is the one that will behave like that. Otherwise, most of the bases, apart from sodium hydroxide, potassium hydroxide, and ammonia solution, will not really dissolve in water. So the definition will not apply to them. Now, having said that, we want to take this a step further. And now that acids will dissolve in water to produce hydrogen ion, and therefore, once the hydrogen ions have been produced, they will react with metals to produce hydrogen and a solid. Now, I want to investigate the reaction between acids that are of the same concentration. 1 molar sulfuric acid, 1 molar ethanoic acid, 1 molar hydrochloric acid, and I want to investigate how fast they react with metals. Now, from that, we shall again come up with an even more interesting concept, idea about the ionization of the acid to produce hydrogen ions as the only positive ions. Hello viewers, in this experiment, the rate of the reaction between 3 different acids with magnesium ribbons is going to be investigated. The 3 acids are hydrochloric acid, sulfuric acid, and ethanoic acid. All the acids are basically 2 molar, and therefore we would expect them to react the same rate. But let's see how the rate of the reaction between the 3 acids compare. So I will introduce a piece of magnesium ribbon into each one of them. Let me start with the ethanoic acid, sulfuric acid, and hydrochloric acid. And there you are. We can hear some fizzing. Some hydrogen gas is being produced in the three beakers. Yeah, the reaction with ethanoic acid appear to be quite slow, and you can bear with me witness that the reaction with sulfuric acid appears to be fastest. Yes, and bubbles are produced. Let's see, and there we are. The reaction with sulfuric acid is over. 2 molar sulfuric acid took the shortest time to react with the magnesium ribbon. Now let's see Which one will be faster, hydrochloric acid or ethanoic acid? And the reaction continues. Oh yes, the reaction is over. Hydrochloric acid has reacted with the magnesium ribbon. We don't have any more of it, so that one comes next. The reaction with the ethanoic acid looks quite slow. That is the experiment, and the observation that we make is that sulfuric acid took the shortest time. So it's the fastest of the three acids. Yet all of them had the same concentration. They were all 1 molar. They were all 1 molar sulfuric acid, 1 molar hydrochloric acid, and 1 molar ethanoic acid. See that sulfuric acid is fastest. Now this is a reason. Whereas the other acids were monobasic, sulfuric acid is dibasic. What do you mean by that? A dibasic, the basicity of an acid refers to the number of replaceable hydrogen ions per molecule. So sulfuric acid has 2 replaceable hydrogen ions. It is dibasic. Therefore, when you dissolve 1 mole when you dissolve 1 mole of sulfuric acid in water, it produces 2 moles of hydrogen ions. And of course, the rate of a reaction depends on the concentration of the hydrogen ions. So it happens to be the fastest because it is dibasic. The others are monobasic, so they will produce 1 hydrogen ion per mole. Note that when you write ethanoic acid, okay, you can write ethanoic acid like that. So it appears to have 4 replaceable hydrogens, but as the case is with organic acid, the number of hydrogen in the molecule is not necessarily equal to the basicity of that acid, because the active hydrogen is the hydrogen on the carboxyl group. This is the active hydrogen. These hydrogens are not active. So this acid is actually monobasic, just like hydrochloric acid, just like nitric acid. They are all monobasic acid. They have 1 replaceable hydrogen. So we have easily explained the rate of the reaction with sulfuric acid. It is dibasic, so it produces more hydrogen ions. But what about the other 2 acids? Ethanoic acid and hydrochloric acid. Why is it that hydrochloric acid is faster than ethanoic acid? And the answer to that can be found in what we now call the strength of the acid. So hydrochloric acid is a strong acid, whereas ethanoic acid is a weak acid. In Form 1, we defined the strength of an acid in terms of the pH. So we said a weak acid is one that has a pH of 5 or 6. A strong acid is one that has a pH of 2 and 3, 1, 2, and 3. So that was the Form 1 definition that we want to render absolute now. So our definition from today henceforth for a strong acid and a weak acid shall be: a strong acid is one that undergoes complete ionization. Please note, no more pH. A strong acid is going to be defined as one that undergoes complete ionization when dissolved in water. So that when you represent the dissolution of hydrogen chloride in water, it will strictly form that and that. Just there is no reversibility of that. Every molecule of hydrogen chloride will convert to a hydrogen ion and a chloride ion. There will be no molecules of hydrogen chloride in a solution of hydrogen chloride in water. Now, all amino acid therefore will be strong acid. They will ionize completely. Now, weak acid on the other hand is an acid that undergoes partial ionization. It undergoes partial ionization, so that when you dissolve this in water, it will ionize reversibly to form the ethanoid ion and the hydrogen ions. In fact, from experiment at 25 degrees Celsius, only 4 out of every 100 molecules will ionize. So mainly there will be molecules of ethanoic acid in the solution of ethanoic acid, not the oxalate ion, not the ethanoic ion, not the hydrogen ion, but mainly the ethanoic acid molecule. So it undergoes partial ionization or dissolution. So note that this is reversible, so that all these will exist in equilibrium. Now, therefore, we define a weak acid. Note, a weak acid is one that undergoes partial ionization. A strong acid is one that undergoes, complete ionization for strong acid. Weak acid will undergo partial ionization. So there are a number. Organic acids will fall under this category, and carbonic acid too. It will be a weak acid. It will be a weak acid in the sense that it will ionize partially to form the carbonate ion and the hydrogen ion. So similarly, bases can be classified into either strong or weak. A strong base will undergo complete ionization. A weak base will undergo partial ionization. So an example, one of the main examples of a weak base is ammonia. It undergoes partial ionization to form the ammonium ion and the hydroxide ion. So that is our new definition of strong acid under strong bases, weak bases and weak acid. So the previous definition will no longer be useful henceforth. We continue our study on acid, bases, and salt. Having defined an acid, having defined a base and the basis of the ionization to produce hydrogen ions and the ionization to produce hydroxide ions, and having talked about the strength of acids and bases, we proceed to look at something else: amphoteric oxides and hydroxides. Now, the word amphoteric is derived from the word amphi, which means both. So, as the name suggests, therefore, amphoteric oxides and hydroxide will have both acidic and basic character. For instance, it is normal for zinc hydroxide to react with nitric acid to form zinc nitrate and water. We shall call that a neutralization reaction. It will be just an ordinary reaction. But the question we ask ourselves is, will zinc hydroxide react with sodium hydroxide? Because if it does, then it will be acting as both base and acid. And that becomes the basis of our next investigation. We shall look at various ions, various metal ions, and add sodium hydroxide. When that is done, a hydroxide will be formed. Then we shall find out whether that hydroxide can react with more of the sodium hydroxide. And